the start of this physics fight. And my name is Wenqin Lin from National Taiwan Normal University. So it's my great pleasure to chair this section of physics fight. So I think that we start from the introduction of our jury. The first one is Professor Li Yingde from Hongjia University. Second one, Professor Gan Hongzhi from Zhongzheng University. Professor Hong Mingguang from NTNU. And Professor Zhong Daijiang from Guohang University. Okay, so now please the three teams introduce yourself, your team member. Let's start from our reporter.
We are Variable 2 from Kaohsiung Girls Senior High School. I'm the leader of the group. My name is Wu Yongshan. This is Gui Yuping. This is Wu Yizhen. This is Liao Yaojun. And this is Wang Luojia.
Okay, thank you. Then our reviewer.
I'm captain of the team sales here, and my name is Ming Xuanqi, and this is Su Datong, and this is Liu Helong, this is Zheng Zhongyang, and this is Jian Kuaishen. Thank you.
Okay, thank you. And our opponent.
I'm the captain of the Laifeng Duojin. My name is Cai Bingyi. This is Xu Weichen. This is Su Yirui. This is Li Chenggang. This is He Yi. Thank you.
Yeah. Okay. Thank you. Thank you for the introduction, and I hope the three teams can enjoy this afternoon's physics fight. So I think that we can start the first stage. So the opponent, you have 1 minute to raise your challenge. Question 1. So the opponent challenge question 1, problem 1. Reporter, you have 1 minute.
Reject.
Yeah, you reject. So the opponent, number 15.先等一下，要不然你没办法意思。还要计时。
We accept.
Okay, so the problem number 15. So reporter, you have 5 minutes to prepare your presentation.
15分，一还可以，一的话要看情况。
Good afternoon, everyone. The problem I would like to present today is number 15, willing bowl. This is the problem statement. When you strike the side of a metal bowl containing some water, you can hear a characteristic sound. The sound changes when the water in the bowl is moving. Explain and investigate the phenomenon. So my main point will be focusing on changing the different variables, for example, the water amount or moving the water, to investigate how that would influence the frequency. These are my theory, and I would use this one in the later slides to explain why the volume of water would change the frequency. And these one too, when the moving of water. Let's just skip them for now. I would have some more detailed explain in the later slides. This is my experiment setup. I had a steady base with 2 bars standing on top. That's where I tied 2 strings to and hung a metal ball. By hanging the ball with 2 strings, I can keep it steady when swinging. So when the ball hits the container, it transfers a force to the ball to the container and forces the container to shake, causing damping force and elastic force in the ball. However, when you pour liquid into the container, the added liquid is forced to participate in the vibration of the container wall. When the ball hits the edge of the container, it causes the whole bowl to shake. The container then conveys the force to the water. So you can see that the wave started from where the water touched the bowl all the way to the center of the water. You can even see the vibration and the waves on the surface of the water. But eventually, the water will return to calm. Yet, you can still see from the water that the inertia remained acting for a little while. This is my data. In the first experiment, I adjusted the volume of water to investigate the changes in the frequency of the bowl. The horizontal axis represents the frequency, represents the water volume, and the vertical axis represents the frequency. So in this graph, you may notice that by adding more water, it causes the frequency to decrease. And the curve is actually slower at the beginning, but steep in the later stage. This formula shows that the frequency F decreases as the amount of water V increases, and the decrease comes progressively faster because both the numerator and the denominator vary with V. You can see it here. Also, during the initial stage, the amount of water is small, and the vibration mode of the bowl is actually determined by the structural characteristics of the bowl itself. The influence of water is small, and the frequency change is gentle. In the later stage, however, when the water volume increases to a certain level, the inertia and the fluidity of the water will begin to dominate the vibration mode, so the frequency decreases faster. This is the second experiment. I added the measurement of frequency change over different water volumes, but at the same time I stirred the water in the bowl circularly. Then I compared the results with the former experiment and found that under the same water volume, the frequency is actually lower when I stirred the water. This is my explanation. The rotation of the water increases this, which is the additional mass caused by the rotational motion of the water. Because the rotating water has additional dynamic effects on the bowl that change the way the bowl vibrates. Also, stirring the water will affect the standing wave pattern and frequency splitting. In still water, the standing wave pattern is determined by the geometry of the bowl. Rotation breaks these symmetries, causing the vibration patterns to become more complex. And the frequency splitting. Rotation can cause a single vibration frequency to split into multiple frequencies, further reducing the dominant frequency. In the third experiment, I added the record of frequency change while I stirred the water irregularly and compared it to the other two. So it is apparent that when stirred irregularly, the bowl excites at an even higher frequency, you see the green one here, than the other two, which is quite interesting. Irregular stirring will cause chaotic fluctuations on the water surface, which continuously changes the movement, direction, and wave pattern of the water, causing the movement of the water to have a complex and unstable impact on the structure of the bowl, making its movement more complex and higher in energy. Therefore, the kinetic energy of the water will increase and cause the vibration frequency to increase. Irregular agitation can involve several different frequency components. These components add to each other on the surface of the water, creating more complex wave patterns. Due to the interference of these waves of different frequencies, the wave number will increase and thus increase the frequency. When you stir water irregularly in a circular motion, water waves propagate across the surface of the water at a steady frequency and in a regular pattern. The frequency of these water is therefore relatively stable and the wavelength is relatively large. However, when churned back and forth irregularly, this creates more complex wave patterns on the water's surface with smaller wavelengths. It is possible that these irregular fluctuations more easily match the bowl's resonance frequency, exciting the bowl's vibrations and intensifying it, potentially resulting in higher frequencies. Since I controlled the speed I stirred the water circularly, I did an experiment 4 to investigate how different speed of stirring would affect the frequency. And I found that when I stirred at a higher speed, the bowl excites lower frequency compared to stirring lower. And this is my discussion. The faster the stirring rate, the more turbulence and movement of the water will occur, and more of the energy will be dispersed into the movement of the water rather than the vibration of the bowl. This can be described by the damping ratio, zeta. When the stirring rate increases, the damping coefficient C will increase, further causing the vibration frequency to decrease. This is the conclusion. I concluded my experiment results. The tendency of, while adding water, the tendency would go from slow to steep, and more water will cause lower frequency. When I stir circularly, the lower frequency than still water, and stirring irregularly will cause higher frequency than stirring circularly. When I stirred faster, it caused lower frequency. And although this whaling bowl problem is a complex non-linear problem combining acoustics and fluid mechanics, we can still conduct experiments and report the results. By analyzing the data, we're able to conclude several relative relationships between variables. There's no simple theoretical solution for this water ball coupled problem, yet we can explain the phenomenon by using some simple physics theory and also confirm our assumption. This is all for my report. Thank you for listening.
Thank you. So, the opponent, you have 2 minutes to ask questions.
First question, could you please turn to page 3?
This one.
Do you derive this equation by yourself or do you found in others' research?
I found it on the other research.
Okay, then turn to page 18. Why does water movement create condition of mass?
Because it had additional dynamic effect, and that will influence the couple of the water and the pole, and further will increase like some kind of additional mass.
Okay, and to page 19. And how did you stir irregularly with the
Irregularly? But irregularly is not talked about in this
page?
page.
20. Sorry, page 20. You say you stir irregularly, but how did you do this?
Oh, I turn back and forth. Not circular.
Okay. And did you stir circularly by hand or by something like stirrer?
I had a little motor so that I can control the speed.
Okay. Then page 11. I want to ask, what is the result of the damping force in the ball?
The result of the damping force. Resource of the damping force. Because I
So we'll stop here. Yeah. So 3 minutes for the opponent to prepare your presentation. Opponent, please take the stage.
Okay. I'm the opponent team, the control team. I'm going to hold the problem 15 very tall. This is a problem statement. When you strike the side of a metal ball containing some water, you can hear a characteristic sound. The sound changes when the water in the ball is moving. Explain and investigate the phenomenon. And the key points are sound frequency and moving water. This is the overview of the report. for the theory part, they use the frequency, kinetic, and wave number formula to explain the phenomenon. Also, they consider damping in their theory. And for the experiment part, they detail explain of how the experiment is done, and they do the experiment for still water, stir water regularly or irregularly, and for the different stir speed. And for the conclusion part, the tendency makes frequency slow to deep, and stir irregularly high. Stir irregularly make the frequency higher, and the more water cause the lower frequency. The stir circularly lower the frequency, and it will that stir faster, the frequency will be lower. And these are remarks to the reporter. For the advantage part, they show the experiment and chart clearly. And this is our suggestion. The first one is they didn't talk about why do they change these parameters, what's the ends. And the second one is no, you didn't compare theory to experiment. And the third one is the lack of parameters. The final one is lack of explanation of theory. Okay, thank you. Now I invite the reporter. Go. Did you use pendulum to strike the ball, right?
Some kind of.
Some kind of. What is that?
This is my, let me show you my experiment set. This.
Yes. Oh, so do you control the height you put the ball?
Oh yes, I actually tied a string from these points to somewhere here, and every time I pull the ball, I will let the string match the string I already tied to. So to make sure the angle and the height, I let go the ball.
Okay.
Ball.
Then the next question is the sound frequency is the main point in the problem. So how do you measure frequency? Because you didn't mention that in your report.
Oh, I used at first I used VFox, but it won't provide accurate data. So I changed to another app, which is not very common, and I forgot the name.
But how did you know the data in VFox is not accurate?
Because every time I strike the ball, the result is 1,000 hertz. And every time, however I change the variable, the result is always out there. Yes.
So you think it's not accurate. Okay, and the next problem is also about the experiment. So you use the ball to strike the ball in the water, in the ball with water. And do you control the strike position?
Yes, of course, because I kept the height of the ball stable, and I kept the space and the distance between the ball the same. So every time I controlled everything I could control, and so it will hit the same place at the ball. Because if it hits the different place, that will probably influence the frequency.
Okay. And the next question. Parameters. And you stir the water for experiment, but it doesn't show in your theory like moving water. So why did you want to do this experiment?
Because this is from the problem statement. The sound changes when the water in the bowl is moving.
But there are many moving modes such as surface wave or stir or go back and forth. So do you need other kinds of moving mode?
I stirred it circularly, and it also caused surface wave. Some kind of. I mentioned in the other slides.
Oh, okay. Let's part of the question. Data. This can do the vessel experiment itself.
First experiment. This one.
Yes. So why the slope is bigger here and it's smaller here?
Oh yes, I mentioned it here, and I explained it in with this discussion because you can see when my v increases, the denominator will increase, and the numerator will decrease. And as the v increased more, this will decrease progressively, and so the f will decrease faster in the later stage. And also, when the water is not so much in the former stage, the bowl structure actually decides the frequency more.
That brings us to the last page.
Last page?
Like,
You mean the conclusion?
the fourth portion. Page 4. First experiment result.
This is the first experiment result.
And the formula.
This one?
Yeah, this one. I think there is a problem in this formula because this is a square root, and if you add a lot of water in the bowl, maybe this will be minus, and there will no real root. Did that happen in your experiment, or you avoid this?
Because the stiffness of the water is quite big, and it actually will be times the volume of the water in the numerator will actually be times the C constant, and it's related to the shape and the material of the bowl.
So
So
it
it will
won't happen
influence.
in real world experiment.
Real world experience. I didn't show my actual data here. So
Okay, the next question. For the second experiment results. Okay, so
yes, please.
it's this is the S is just the volume of water, so there's oh sorry. Actually, how fast do you stir in this experiment?
Oh, I stirred, I believe it is 3 circles in a second.
And for the result of experiment 3,
This one?
sorry, it's not this one. For the results of stir speed
Oh, this one.
on time. The first question is why did you only do 2 data?
Oh, no. This is just the example.
Oh, this is all. Yeah.
Yes, I only put part because I want to enlarge the graph. If I put too many data here, you won't see it clearly.
Oh,
And I only took part. I think this is, you can know the relation. I just want to show it.
there.
No, I didn't put the graph.
I didn't do that.
Because I already compared the frequencies in the former experiment. Different frequencies.
Yeah, but different frequency means the stir angular speed or the sound frequency.
I didn't talk about the angular speed.
Stir frequency.
Stir frequency? You mean the frequency
3 circles per second,
3 circles?
like that.
Could you say it clearer?
The final one is and so if the angular speed is going bigger, the frequency will be smaller, right?
Yeah, in my result.
And what is the mass relationship between them? Is it proportional or something else?
You mean why caused this result?
The mathematical relationship between them.
Oh, I said that there's not a linear solution for every result in this problem because it is combined with the acoustic and fluid mechanics problem and the coupled of the bowl and the water. So I could show the relationship between them and I could deliver my possibility results, and these formulas could actually explain it. But I believe there's still more and more parameters that could influence this.
And for this part, you consider damping in your theory, but did you do experiments about damping?
Experiment about
Yes.
it. I could kind of experiment.
Like to change the damping coefficient.
Damping coefficient, you mean? But when I stir irregularly and circularly or not in different speed, it actually changes the coefficient because it's related to the movement of the water. So I did change the damping coefficient. That's why the frequency changes.
So did you know how the damping coefficient changed when the water is moving?
Yes, I explained that. When I stir faster, the coefficient will increase, and so the damping force will increase, and further causing the frequency under damping will decrease.
Okay. And this and experiment one result of experiment one.
This one?
Yes. I see the formula you give for this experiment, but I think maybe in that formula, the graph should be like this. The slope is bigger here, but it's smaller here.
Why do you think?
Because the next page.
This?
Because this is plus and it's minus here.
Yes.
So when the B is bigger,
Yes.
the change will be smaller.
The change.
Because this part is bigger and this part is even smaller, so the change should change smaller.
Yes, this is smaller.
But in your experiment result, the frequency change bigger when the volume is bigger.
No, no,
right?
no, no, no. No. Look at this graph.
Yeah.
It is actually smaller, decreasing.
I say the slope is bigger.
No, this doesn't represent the slope. This is just the frequency. I showed the frequency. This is where the frequency formula, not the slope.
And so if the volume gets bigger, the slope of frequency must be smaller.
Yes.
Yeah,
No,
but
no, no, no. Huh? Could you say that again?
When the volume is bigger, this part is bigger and this part is smaller.
Yes.
So the slope should be smaller.
However, I considered another thing, that in the initial stage, the bowl will actually dominate the frequency and it won't change that much. On the later stage, the water fluidity and inertia will dominate the frequency and it will change the frequency more progressively.
Okay, so time's up. So the opponent, you can summarize your discussion for 1 minute.
Okay, this is a summary of our discussion. The first part is about the instrument setup. The first experiment setup, and we also talk about the detect of the frequency. She said the feedback, and also use another tool to get a more accurate result. And the first part is the force speed to the ball. That she used a thing similar to pendulum to strike the ball. And also we talk about why the reporter chose this moving type, because she said it's mentioned in the problem and they choose the stir type. And we also I talk about the breadth slope. It should be bigger to smaller, but the result is smaller to bigger. And actually I didn't get the accurate
Sorry,
answer.
time's up. So now is the reviewer.
For your opponent, what deviation do you think the experiment might cause? what deviation might cause?
Deviation, for example, the frequency sensors deviation,
Yes.
or the maybe
What
the
kind of-
water viscosity.
Oh, okay, thank you. Do you agree with his opinion?
He's
Like
About
water
the-
viscosity?
yes, please.
Okay, never mind. Question to the reporter. Since you didn't have the theory line, and can you calculate the K, which is the stiffness in your experiment?
I
Can
didn't,
you-
but I could.
Okay, thank you. Do you think calculating the K, which is stiffness, is important to the experiment?
I think if she control the experiment condition well, the K won't change, so she can just compare the different result.
Okay, thank you. Question to the reporter. Since you mentioned about there will be multiple frequency in the water, right? And can you quantify the frequency multiply of the water?
If I use the Ferrari and use the spectrum, I can actually know. But actually, the dominant frequency you can see in every spectrum. So I only pick the dominant frequency to
Okay,
discuss.
thank you. Do you think the multi-frequency of the water will affect the phenomenon?
The problem standard is that the frequency will change when the water is moving.
So will
But
it
the
affect?
frequency here is the sound we hear. So we actually hear the multiple frequency add together, and then we hear it. So
Is it
maybe
important?
it's not. Maybe we could just analyze the biggest amplitude one.
Okay, thank you. Can you define what is a damping force? And can we quantify it if we want?
Maybe because the ball will vibrate,
Yes.
and the water may resist it.
So can you quantify it? Can we know how much is the damping effect? No. And to the reporter, can we know how much the damping force is?
But the damping force is actually changing, always changing.
Yeah,
Because
but can we know how exactly is it?
Is there the need to calculate that?
Oh, okay. Thank you. It's okay. Can you control the initial position to strike the ball?
Yes, I said.
Okay, thank you. Will the type of mentor used for the ball
Sorry,
influence the sound
time's
produce?
up. Viewer, you have 2 minutes to prepare your presentation.
Honorable judges and fellow competitors, I am the reviewer from Team Excelsior. Today, I'll be reviewing number 15, welding ball. This is a problem statement, and today we are going to put our main focus on how do we strike the metal ball and move the water, and how do we define sound. This is the review of the report, and this is the theory the reporter used, and this is the experiment parameter she did. She had the demonstrative phenomenon, however, she is lacking a lot of potential parameters. Also, the experiment data are lacking error bar, so we didn't really know how much time the reporter did the experiment. And also, she didn't provide boundary in those kind of cases. Next, they didn't explain where the sound came from. Is it from the water or from the metal ball? Next, they failed to define sound. Sound is a complex. It has amplitude, frequency, and like many type of aspects. And they also failed to quantify the damping effect, and also failed to show some observation video. They have an oversimplified theory, which did not have a theory line and no analysis. This is a review of the opposition. The opponent noticed the lack of parameters and lack of experimental setup. Like setup is like how they control the ball, like manually or by device. Next, they failed to discuss the lack of boundary conditions. This is the discussion. The opponent asks what is the frequency the reporter stirred the ball, and the reporter answered with 3 circles per second. However, the reviewer thinks that the reporter should provide an observation video of the experiment, and also conducting the experiment manually may cause deviations. Next is the damping effect. The opponent said that the reporter mentioned damping in the experiment, and the reviewer thinks that the reporter should quantify the damping effect, not just saying damping without any experiment data. Next is our question. We asked what deviation could the setup cause. And next is we asked how is the K, which is the stiffness in the theory of the reporter. And the opponent said it is just used to compare different results. And the reporter thinks she didn't quantify the K. Since the reporter had mentioned there will be multiple frequency on the water, so the opponent said that the multiple frequency has to be discussed with its biggest amplitude, and the reporter picked the dominant frequency to do the experiment. And this is the point missed. About setup, they missed discussing about temperature consistency, because higher temperature or lower temperature could affect the viscosity of the water, which might lead to surface tension. Next is the parameter. The method of shaking the ball could also be investigated, because we can spin the ball like this, or also we can spin the ball with a rope. Next is the material, size, and shape of the ball. And the spinning speed of the water should also be considered, and the size of the ball. And the direction, the frequency of striking should also be considered. Last is the sound. We really need to define the sound, because sound is complex. It has frequency, wavelength, wave speed, amplitude. And the experiment has to ensure the sound itself. So
Reporter, please conclude.
Yes. This is my concluding remark. First, I would like to clarify some questions. How to stir regularly? We use a little motor. And why vibrating water causes additional mass? It's when we stir water, the rotation of the water will cause additional dynamic effect and influence how the water moves. Could I explain the tendency of your frequency data? Curvature is small at the beginning and water volume is quite little. The ball affects frequency more obviously. Will first experiment formula turn to negative? No, because we have another parameter to control. Did you do experiment about damping? The damping coefficient changes by the vibration of the water. So it's no need to measure the damping coefficient because we're mainly focusing on the frequency. What's the tendency damping coefficient change? when I stir faster, damping coefficient increases. Can I quantify the frequency? Quantify the frequency? Yes, I did quantify the frequency. Can I calculate the damping force? It's hard but possible because the coefficient is continuously changing and there's no need to do so. And I would like to answer some questions from the reviewer. He said I didn't set the boundary, but I didn't state different stages, so there's not actual boundary. I just changed experiments and variables. And he asked, where did the sound came from? I think the sound came from the bulb because you can see from my graph that when I put zero volume of the water, and I strike it, there will still be the frequency, and it's the natural frequency of the wall. But however, our experiment showed that adding water into the bowl will influence the frequency actually. And he asked me to calculate the K, but I said yes, but I can calculate the stiffness of the bowl. Thank you.
Thank you. So the three presenters, please come to the stage. Now it's time for jury to ask questions. Any question from our jury?
For the formula you show the frequency as a function of the volume of water in the bowl, is it a guess or is it from a book or from a reference?
It is from a reference.
So which is the reference?
The paper that is, I believe it's the paper provided, or the other paper with the acoustic and bowl.
So in that is the reference?
Um,
And then for the movement of water that affect the frequency, is it the effective mass which you use, or is the damping? You show two possible reasons, and which one is it? So instead of water, you say it's a damping, but go back, you say when the water is moving, there is an effective mass and EFF. So which one is yes? So which one is the one that caused the change of the frequency?
they all cause the change of the frequency. And from these formula I showed, we could see the related relationship.
How you see?
I explained because
No, how you see? So quantitatively.
No, not quantitative.
So you guess, is that right?
Not really. Because I can see relatively. Because
What do
you
you
cannot-
mean by see?
because the data cannot be put into a formula and will exactly fit it.
There's no way you can put number in EF anyway.
Yes.
Any other question?
I have a question to the opponent. I know you have challenged the reporter about the equation about the slope, right? So do you think that equation can offer us the slope mathematically, just pure mathematical question?
I can do differential and I will get a slope.
So ideally we should be able to get a slope. That's what you teach. Have you ever done that during your presentation?
Not really.
Do you agree with what he said? Getting the slope from your theoretical formula here, and hence compare that result with your experimental data on the slope.
I don't think we could get the slope.
What I'm saying is when V is very small, the slope is small. When V is getting larger region, the slope is larger experimentally.
Yes, I think it's like that.
But you didn't really do the differentiation, did you?
Because when this will be small and this will be big.
You have to do the mathematical, right?
Yeah. But I put another theory to explain that too.
Thank you.
Sorry for that.
Any more questions? Professor Fong?
Just a question for the reporter. Have you recorded the sound? What does it sound like? What is the difference? Usually record the sound and then
Show it? Oh,
the
sure.
sound.
Oh, I could add that in the other.
So what's the difference if the water is moving? So can you see the difference by the year?
Actually, very slightly, because the frequency only changed a little bit.
Any question? No? If not, okay, so the jury please prepare your score. So ready? So for the reporter, 5, 6, 3, 6, 6. And for the opponent, 5, 8, 8, 6, 5. For the reviewer, 6, 7, 4, 8, 8. And so if any jury would like to comment?
Yes, on the reporter, I think when you report, I don't expect you read from your note. You should speak to your audience, not just read from your report. Secondly, when we ask you questions, you have to answer quantitatively. And when you see something and there's no proof, which is not acceptable in your presentation. And you have equations, you have your data. The simplest thing you can do is to fit your data to the equation. Then you can get all the numbers, whether the number make difference or not, or make sense or not. But what you keep saying in circle is, when you say big, you say small. When you say small, you say big. And you feel and you see it. And so it's very hard to understand what you try to convey in the information. You did not show your real data, so you show how you strike the ball, but you never show a frequency map and show us how the frequency will change, the peak will change with some of the parameters. Not every single data, but at least you should demonstrate to the audience that you have measured the sound frequency, that is sound spectrum, and you did not describe only after being asked how you measure the sound information. So, which in a sense, the report is really below average.
Other comment? No? Okay, so let's finish this stage and then take a short break. 10 minutes back.